Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Today we want to talk about trig equations again. This time we want to talk about multiples of angles. What do I mean by multiples of angles? I mean you're going to take an angle and you're going to multiply it by something. This is an equation where the input, the argument of sine, is a multiple of x. Like before, there's two ways I can ask you to answer this question. I can ask you to find all the solutions, or I could ask you to find all the solutions between 0 and 2 pi radians. Now, unlike previous trig equations, it's actually going to be the second one that's harder. Normally, it's a tiny bit harder if I ask you to find all solutions, because then you got to say the plus 2 pi k, right? But here, as we'll see, we have to pay attention when asking for all the solutions between 0 and 2 pi. So how do I do this? How does it work? Well, you know that if you have sine of omega equals 1, what we're supposed to do with this, right? You look for the angles for which sine is equal to 1. And so you say, well, gosh, where is sine equal to 1? When omega, the inside, is equal to pi over 2. Or, finding all the stuff ever, we would say plus 2 pi times k, where k is any integer, right? Now, all we have to do for this is basically a substitution. We think of this as one whole group. We can think of it as a new letter, omega, right? We know that if the inside is pi over 2, then sine of the inside will be 1. Whether that inside is a single letter or an expression doesn't really matter yet. So just like this equation says that the inside has to make sine equal to 1, so the inside must be pi over 2 plus 2 pi k here, the inside has to make sine equal to 1, so the inside must be pi over 2 plus 2 pi k. The difference being is that the inside, again, is no longer a single letter, but an expression. So, to find all solutions to this equation, we have to continue solving for x. That's basically the only thing we didn't have to do in this simpler equation. So, to continue solving for x, we got to get rid of this 3. The opposite of times 3 is divided by 3. Or, if it's helpful to you, multiplying by the reciprocal of 3. Dividing both sides by 3. Or, equivalently, multiplying by the reciprocal of 3. Pi over 2 divided by 3? Nah, pi over 3 times the reciprocal of 3. And 2 pi k divided by 3. Well, that's fine. Let's just go ahead and divide that by 3. But when we see this product of fractions, it gets to be pi over 6, and this is 2 pi k over 3. This is one of those things that trips people up on this kind of problem. They forget to add the 2 pi over k before dividing both sides by 3. And they're going to miss out on lots of solutions. 2/3 of them, in fact, because pi over 6 is a solution. When I plug in pi over 6, I get 3 times pi over 6, which is pi over 2, and sine of pi over 2 is 1. Marvelous! But we'll see this now that I'm going to ask you for all solutions between 0 and 2 pi. Normally, here, there's only going to be one value of k that will make an angle, omega, between 0 and 2 pi. 0. If I say k equals 1, then this becomes pi over 2 plus 2 pi, which is automatically greater than 2 pi. Right? Now, here, we're going to plug in a bunch of k's. I'm going to start with k equals negative 1 up to k equals 4. And we'll see which of these are between 0 and 2 pi and which ones aren't. So what is k in here? K is supposed to be any integer. Any integer k is supposed to make this a solution to the equation. Integers. So what are integers? Well, that's the natural numbers, 1, 2, 3, 4, 5, etc. But also 0, but also the opposites of all the natural numbers. So let's take a nice, easy one to start with. negative 1. What happens when k is equal to negative 1? This is x equals pi over 6 plus 2 pi over 3 times negative 1. Well, multiplying this by negative 1 is just going to make it negative, right? So pi over 6 minus 2 pi over 3. If you get these guys a common denominator, the common denominator we want, the least common denominator, is 6. What do I have to multiply 2 pi over 3 by to make it equivalent, but have a denominator of 6? 3 times what equals 6? 2, right? So this is going to be pi over 6 minus 4 pi over 6. 1 pi over 6 minus 4 pi over 6, 1 minus 4, negative 3 pi over 6. But this is reducible. It's negative pi halves. Is this between 0 and 2 pi? No. So k equals negative 1 does give you a solution. It does not give you a solution between 0 and 2 pi. So we're going to skip this one. So let's try the next integer. K equals 0. K equals 0 is one that you should pretty much expect to work every time. When k equals 0, multiplying by 0 gets you 0, so pi over 6 plus 0 is just pi over 6. That's definitely between 0 and 2 pi. And when I plug it in here, you should also notice that this is a solution. Marvelous. So let's try the next one. K equals 1. When I plug in 1 for k, I get pi over 6 plus 2 pi over 3 times 1. Multiplying this by 1 gives you 2 pi over 3, gives you back what you started with before the multiplying. 2 pi over 3 plus pi over 6. Since we've already found the least common denominator, this time we have the positive version instead of the negative version, we're not going to do all the hard work again. So we get 1 pi plus 4 pi over 6, which is 5 pi over 6. This is also in 0 to 2 pi, so we'll put a nice little box around this one too. Notice that unlike this equation, where only one k value gave you a solution between 0 and 2 pi, this equation already has two solutions. That's more than one between 0 and 2 pi. Let's try k equals 2. This means x equals pi over 6 plus 2 pi over 3 times 2. What's the denominator of 2? Well, the denominator of 2 is 1. That's the only number I can divide 2 by and still get 2. 2 divided by 1, yeah? Right, great. So multiplying 2 pi over 3 by 2 means multiplying 2 pi over 3 by 2 over 1. Top times top over bottom times bottom. We still have to get a common denominator. We still have a pretty good idea what that common denominator is and what I have to multiply the top and the bottom by, but the result will be different this time. So pi over 6 plus 8 pi over 6. The result is 9 pi over 6, and this reduces to 3 pi over 2. 3 pi over 2 is also between 0 and 2 pi. So this is a third solution that is between 0 and 2 pi. Now I would like you to find x when k is equal to 3 and find x when k is equal to 4. Try it. Pause this and I'll wait here. So I bet you probably don't think I actually wait because I'm recording this. I don't have to wait. I wait every time. I go get a drink of water, have a sandwich. Here we are. We've got k equals 3 and k equals 4. You'll notice that right here it says 2 pi plus something. This is automatically bigger than 2 pi. This is not in 0 to 2 pi. This is bigger. It is also not between 0 and 2 pi. But they are solutions to the equation. They're just not between 0 and 2 pi. So solutions to this equation between 0 and 2 pi are these three dudes. Okay, campers, it's time for example 2. Find all solutions to this equation in the interval 0 to 2 pi. 2 times sine of 5 theta plus radical 3 equals 0. Like other trig equations, or many other equations, the first thing we want to do here is isolate the thing that makes it tricky. Isolate the trig function. So that means we've got two terms, we want to get one of them to the other side. Things that we can do. We can multiply both sides of an equation by the same thing, or we can add the same thing to both sides of an equation and get equivalent equations. So to get rid of this second term, we're going to add its opposite, negative radical 3, to both sides. 2 times sine of 5 theta equals now negative radical 3. To isolate this expression and to get rid of the coefficient, so to undo times 2, we will say divide both sides by 2, or multiply by the reciprocal of 2, if you like. We're going to go ahead and do it this way. 2 divided by 2 reduces the 2's, and now we have isolated the trig function. Sine of 5 theta equals negative radical 3 over 2. Okay, here's the part where we have to say, what do I plug in to the inside to make sine equal to negative radical 3 over 2? We forget about whatever is inside the sine, and we just say, what does the inside have to be to make that happen? Well, we know this is radical 3 over 2, so the reference angle is not going to be pi over 6, it's going to be pi over 3. We know that this is negative, so that our angle has to be in the third or fourth quadrants. So we're looking for things whose reference angles are pi over 3 in the fourth and third quadrants. We want the inside to be either 4 pi over 3 or 5 pi over 3. And we know that in addition to these, we're also going to accept anything coterminal to these. So plus 2 pi k for any integer k. But the thing is that the inside of this was not just a single letter. We're using this to sort of make it easier for the moment. But what's inside that sine function was the expression 5 theta. Now, to find solutions for theta, all we have to do is solve this for theta. So divide both sides by 5. It's really, really important to divide both sides by 5 after adding 2 pi k. And remember that instead of dividing by 5, I can multiply by the reciprocal of 5 if that makes it easier. And for these fractions, I bet it does. So we've got that one over there, but we've also got this one over here. 5 theta over 5 equals 5 pi over 3 times 1/5 plus 2 pi k over 5. And this gives us theta equals 4 pi times 1 over 3 times 5. That's 4 pi over 15 plus 2 pi k over 5. Nothing to do about that. And over here, we've got theta. Now look at this, 5 in the top, 5 in the bottom. That just becomes, well, you could call it 5 pi over 15, which might be helpful for a minute, but it's also pi over 3. It's helpful when we're doing lots of things like this with all the fractions to have the reduced version and the unreduced version in your head, although your final answers should be reduced. Now, this is all of the solutions, period. In order to find all the solutions between 0 and 2 pi, we need to ask ourselves, for which k values is this going to be between 0 and 2 pi? So I'm going to suggest to you, try plugging some k values in. Which ones do you think are going to work? So go ahead and try a bunch of k values and work it out. Pause this and I'll come back to you in a minute. Okay, I'm back. So, are you back? Great. Which k values worked? Did you try k equals -1? How about 0, 1, 2, 3, 4, 5, 6? Did you try anything else? Well, you can't answer me because this is pre-recorded. But some of these should have worked. These ones should have worked. If you tried -1, you should have seen that it was less than 0. If you tried 5 or 6, you should have seen that they were bigger than 2 pi, and none of those would have worked. But all of the stuff in here would have worked. How many solutions is that then? Well, 5 k values for this expression and 5 k values for this expression means 10 solutions altogether. You should also notice that the out of the 5 solutions from this expression, most of them won't actually be in quadrant 3. The theta values aren't guaranteed to be in quadrant 3. 5 theta was in quadrant 3. These theta values aren't. Now, if you haven't found all 10 solutions, now would be a good time to try that. I'm going to do some of these. I'll probably do all of them, let's be honest. And I'll try to leave you more on your own for the next one. So here, we've got these k values and these expressions. K equals 0. This should always be the easiest to plug in. 4 pi over 15 plus 2 pi times 0 over 5. That's 0 over 5, which is 0. So k equals 0 is just 4 pi over 15 for this one. And here, when I plug in 0 for k, you can bet I'm going to have all of this go to 0 again. So we're going to get 4 pi over 15 and pi over 3, which I hope you remember is 5 pi over 15. Now, k equals 1. That's 4 pi over 15 plus 2 pi times 1 over 5. Now we're going to get a common denominator to add these. The common denominator is between 5 and 15, 15. What do I multiply 5 by to get 15? I have already written the answer. So, 4 pi over 15 plus 2 pi times 1 times 3 is 6 pi over 15. And this ends up being 10 pi over 15, which, yes, it reduces. It is 2 pi over 3, but let's also remember that it's 10 pi over 15. So we got 4 pi over 15. We've got 5 pi over 15. We've got 10 pi over 15. We're going to get another solution from this expression when k equals 1. So let's go ahead and do it. We've got pi over 3 plus 2 pi times 1, still, over 5. And we're going to need a common denominator, but the common denominator between 3 and 15, not different from the common denominator between 5 and 15. It's just that I've got to do more work this time. Pi over 3 needs to be turned into, you guessed it, 5 pi over 15. Yeah, we knew that was coming. And then again, this is 6 pi over 15. So when we add them up, we get 11 pi over 15. Cool, right? So we've got 4 pi over 15, 5 pi over 15, 10 pi over 15, 11 pi over 15. What's going to come next? K equals 2. When k equals 2, we've got 4 pi over 15 plus 2 pi times 2 over 5. Again, a common denominator. We already know what I have to multiply this by on the top and the bottom. 3 over 3, right? Except now it's 2 times pi times 2 times 3. So 4 pi over 15 plus 4 pi times 3, 12 pi over 15. And when we add them up, we get 16 pi over 15. Boom. And that was the first of our two expressions. We've got another one to do over here. And we're going to plug in 2 for k, just like we did for the first expression. 2 pi times 2 over 5. Multiplying this one by 3 over 3 and this one by 5 over 5, we're going to get that common denominator. We're going to get it. This guy turned into 12 pi over 15 just like it did last time. That's not the part that's different. It was the first part that was different. And when we do it, we get 17 pi over 15. And when you go ahead and you go through and you do k equals 3 and k equals 4, you should get something that we should come to expect. For k equals 3, you can check your work on this if you want to take a stop and look at it. 22 pi over 15, 23 pi over 15. For k equals 4, 28 pi over 15, and 29 pi over 15. So here are all the things, all together in a nice list. 4 pi over 15, 2 pi over 3, 16 pi over 15, 22 pi over 15, 28 pi over 15, all from this first expression. And then we've got these ones, all from the second expression. And you should notice, if you think about them all in terms of over 15, that this is 5 pi over 15, that each of these is 6 pi over 15 units apart, which is 6 pi over 15, the same as 2 pi over 3. You should also notice that each of these is 6 pi over 15 units apart. You should also notice that if you subtract 6 pi over 15 from this, you will get a negative 2 pi over 15, which is not between 0 and 2 pi. You should notice that if you add 6 pi over 15 to this, 28 plus 6 is 34, which is bigger than 30, right? Yeah, and 30 pi over 15 being 2 pi. So if adding 6 pi over 15 was too big with this guy, it's going to be more too big with this guy. So these are all the ones that fit. And these are all of the solutions. Hopefully, you'll notice that while 5 theta was going to be in either the third or fourth quadrants, this is most definitely in the first quadrant. This is less than it. This is in the second quadrant. These things are all over the place, man. So, just because 5 theta is in quadrants 3 and 4, it doesn't mean theta is, right? Okay, so that's a bunch of solutions, right? A veritable boatload, in fact. We had 5 solutions per expression. And remember that we started with 2 times sine of 5 theta plus radical 3 equals 0. That is linked, for sure. Just like in our first example, we had sine of 3x equals 1, and we had 3 solutions per expression. This time, of course, we only had one expression because the argument had to be quadrantal angle, but 3 solutions per expression, because that was a 3. In general, for equations involving either cosine or sine of a multiple of an angle, cosine nx or sine of nx, using k equals 0, 1, 2, 3, or all the way up to n minus 1, whatever this number is, 1 less, n minus 1, will give you solutions between 0 and 2 pi. The exceptions are cosine of nx equals 0 and sine of nx equals 0. There we go, that's fixed. Why not? Why are these different? Here's an example. Find all solutions between 0 and 2 pi for cosine of 2x equals 0. I made it 2, so there wouldn't be a lot to go around. Remember the graph of cosine? It did stuff like this. And when y was equal to 0, you were on the x-axis, right? That's how that stuff worked out. Oh, great. So, there are 2 places. Here, pi over 2, and here, 3 pi over 2, where cosine is equal to 0 between 0 and 2 pi, and they are exactly pi units apart. You can start by saying the argument has to be either pi over 2 plus 2 pi k, or the argument, the inside of the function, the stuff between the parentheses, 2x, has to be 3 pi over 2 plus anything coterminal to that. But these guys are pi units apart. Now, if you follow the 0, 1, 2, 3, dot, 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 n minus 1 rule on the previous slide, that'll work out fine like this. But notice that since those two were pi units apart to start with, if I turn this into plus pi k, that will take care of both lists at the same time. Everything in here gets dumped into this expression, everything in here gets dumped into this expression. This will take care of both of them. You're going to need more k values to make it work, though. You will have the same number of solutions doing this or this versus this. Now, when I do this one, you should have 2 k values, because this is a 2. You should have 2 k values for this one. So 2 solutions here, 2 solutions here. This one should have 4 solutions. See if you can make both ways work. Try to plug in k equals 1 and k equals 0 to these two, and find all of the solutions between 0 and 2 pi for various k values here. Using the two expressions separately with a plus 2 pi k, we should get k equals 0 and k equals 1, giving us these 4 solutions when we put them all together. Using the unified list that says pi over 2 plus pi k, we're going to get x equals pi over 2 divided by 2 means pi over 2 times the reciprocal of 2, plus pi over 2k. So this is pi over 4 plus pi over 2k. Now when I plug in k's, I'm going to get k equals 0, gives me pi over 4 plus 0. That was easy. But there's only one list now, remember? So that one's finished. When I plug in k equals 1, this is going to be pi over 4 plus pi over 2 times 1. Pi over 2 plus pi over 4, get a common denominator, pi over 4 plus 2 pi over 4. That's a total of 3 pi over 4. That looks familiar, right? And you go ahead and do that 2 more times. And we'll get the same 4 solutions we got the other way. So When we say k equals 0, 1, 2, dot, 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 up to k equals n minus 1, we're talking about doing it with these two separate expressions, so that k only goes up to n minus 1 in this case. 2 minus 1 is 1. That's the maximum k. If you're doing it with two separate lists, but if you're doing it all in one go, because your solutions are only pi units apart, you can do this, then you get twice as many k's, right? Same number of solutions. Some people like having options, some people don't like having options. If you don't like having options, do it this way. And that's fine, because you get the same answers. But sometimes it's handy to be able to express your solutions in one expression. Before we go, I want you to try this one. Try it by yourself first, and then I'll let you check your answers. So go ahead, pause me. I'll go get a drink. And are you ready? Because I'm ready. The solutions to this. Solving for the trig function, the trig expression, cosine 4 theta. And then saying, what does 4 theta have to be in order to make cosine equal to 1/2? Theta has to be pi over 12 plus pi k over 2, or 5 pi over 12 plus pi k over 2. For which k values is this going to work? Well, if this is 4 theta, we suspect that k equals 0, 1, 2, and 3 will work. 4 solutions per expression. 4 solutions from this expression and 4 solutions from this expression. Altogether, 8 solutions. A lot of the hard part of this is adding fractions for most people. One of the other hard things for people is knowing which k to plug in, what is k, an integer, and what it looks like when you plug in k. K values are going to take the place of k in this expression. You just pick k's and plug them in. We have experience to back us up, though, when we have an idea of which k values will work. Most of the time, unless you're using stuff like this, k equals 0, 1, 2, 3, dot, 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 up to n minus 1 will work. And the other ones won't, as we saw in our first and second examples. So, if you know how to plug in k, which k's to plug in, and how to add fractions, it's really not that bad. And then it becomes a trick of remembering to divide both sides by n after adding the plus 2 pi k to get everything coterminal, right? Because for theta, these guys, all these solutions, they're not actually all coterminal, right? That's the tricky part. For the argument as a whole, these things are coterminal to each other, but for the theta values themselves, they weren't. Theta values from two different k values, these aren't coterminal. There's no way that this and this have the same terminal side. For 5 theta, sure, but for theta itself, no. So if you're only expecting coterminal solutions to the first solutions, you won't find all 10 of the solutions to this equation. That's why it's super important you have to add 2 pi k before finishing solving for theta. That's the part that trips most people up, is forgetting to add 2 pi k before dividing both sides by 5. That's all the time we're going to put into this one. Our constellation for the day is Cancer, the crab. Snip, 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 snip. And this has been a Badger Bear production of the Wonderful World of Math. Thank you, and good night!